Good morning to everyone. I, Mohammad Abdul Junaid, coordinator, welcome you all on fourth day of 1 week AICTE training and learning program sponsored by Atal on 3D printing and design organized by Lord's Institute of Engineering and Technology in association with Center for Product Design, Development and Additive Manufacturing, Usmania University, Hyderabad. So I request our speaker. Today we are going to have our speaker, Dr. Shivaram Krishna, Joint Director and Associate Professor from Usmania University, Hyderabad. So he will be giving lecture on 3D modeling on biomedical application of 3D printing. So we have heard lot of about the biomedical. So we will going to have session on biomedical applications of 3D printing.
Thank you for Junaid sir for introducing me to the audience and also for giving the opportunity to share my experience on biomedical application. I would like to present here some of the live case studies that we have done. I am not concentrating on how you do modeling everything because I would like to talk about what are the how we have solved some critical cases using 3D print technology for biomedical application, right? So this a doctor and engineer when they join together, they try to solve some critical cases. So this is what 3D printing brings about different people to come together and work to solve some critical cases for the help applicable to the take an additional hand to the surgeon. So you help as an additional hand to the surgeon. And why 3D printing in medicine is because for visualization curvilinear complex anatomy. So for those things, you can use 3D printing because to understand very complex shape of the body, human body anatomy, you can see it and understand very easily with a 3D printed model. And also you have a physical feel of the area of interest. Other one is you can easily communicate and educate the patient how that injury happened, how that fracture happened, what is the type of disease they are having. All those things you can, and also you can do diagnosis and surgical planning you can do. That is for planning the surgery, complex surgeries, you can use this as a model, right? So you can the creation of customized prosthetics, you can make your own customized and accurate placement of you can do. That means and about how you place implants, everything that you can think about using this technology, right? So the transformations you brought is from a X-ray CT scan. Plans, human anatomy, surgical aids, instruments, scaffolds, and printed organs. Is for a dedicated software like Mimics or 3D. Then from the CAD model, you convert into STL file. From the STL file, you use STL file already you know. Using an RP technology, 3D printing technology, RP, rapid prototyping. Earlier it is known as rapid prototyping. Now it is 3D printing. Using this technology, you produce the final product, and that you do post processing. That is, you do cleaning, curing, or removing everything. Then you get the final model out of it. This is a general procedure for creating medical models. So what is the activities, input, output, instruments, actors are? So for when you want patient, from the patient you get output a CT image. For that, you use a tomography instrument, and the people who are working there are radiologist and the surgeon. Then you have the CT image, you model into 3D CAD model using a dedicated software. They use a computer graphic, a 3D model, CAD model, you have a STL file. Then you're using a stereolithography, you produce the RP model, that is 3D printed model you produce. There you have a rapid protein expert and a surgeon. They will be there, who will be doing that. And then you have an RP model. Then you validate the RP model using, with the help of a surgeon, you validate the RP model. Then you do virtual surgical planning on the RP model. Then you do software for STL editing, and the computer graphic expert surgeon will be there along with you. And then you do virtual surgical planning, that is validating virtual surgical planning using surgeons. Then the relevant measures what you take is physical simulation of surgical procedures, everything you do as a surgeon. And this is the patient you have using everywhere you can see surgeon is along with you. You will be coming as a computer graphic expert, as a mechanical engineering, and as well as a 3D printing expert. You will be assisting doctors in various critical stages of his operation. So that's what you can see in this particular table, right? So let us see how we have solved using 3D printing this particular case study of orbital volume analysis in mid-facial fractures using 3D printing technology, right? So what is that orbital volume? Is you see whenever there is a fracture at the bottom, this eye gets dilated. This eye will be getting affected. The eye region, this is called orbital volume. So what happens is this portion of that, because of the fracture, the eye gets displaced. Because the eye gets displaced, the vision affects. So doctor has to restore it by putting this joining all these parts. He will be able to perform operation joining this, and after 3 months you will observe how this volume has restored. So we are going again. You take a CT scan and find out. You compare this one with unfractured side. This is called unfractured side. All call as what you call contralateral side. This is called contralateral side. So you take this contralateral side, and using these contralateral side dimensions, you measure this one and do this. This is a part of UUC minor research project, and this motor vehicle. How this happens is because of the motor vehicle accidents or domestic violence or sports, etc. This accident will happen, and this is what I am telling you. The mid-face region, that is, you have this region where this actual fracture happens. That's called mid-facial region. So when you want to measure this orbital volume, you use some landmark points called as the mid or medial orbit. Any human body have landmark point. This is called medial orbit. This zygomatic suture. This supraorbital foramen. This infraorbital foramen. You measure these distances, measure the volume. This contralateral side you measure the volume, and this side you measure this volume from this landmark point. These landmark points will be pointed by will be given by the doctor, and we will measure this. So we can say before operation how this amount of volume increase. Naturally, because of this deformation, the volume will increase. So how much is the volume increase because of this deformation? So that you can take care. And this what happens is this volume you compare with this normal volume. So you find out which is what is the percentage of restoration you can do here. So that's what happens here. So zygomatic frontal suture, these are the points you have here, right? So the main aim of this research work is to evaluate the orbital volume during mid-facial fractures using additive manufacturing technologies. And the evaluation orbital volume is done by measuring the dimension between the fixed landmarks on both 3D printed and 3D CAD model of the fractured skull before and after operation, then compared with the unfractured side of the skull to establish the percentage of restoration. So in the present work, we are considering a 28-year-old male patient who has sustained a severe injuries on the midface. We taken the help of S-Face Medical College Hospital. I think Speaker Abhinandan was there. He worked with this. I worked with him, and we have done this work. So this is how the fracture happened to this eye of this person. This left and frontally and right laterally, you can see. For this, we collect the CT scan image of the patient in DICOM format from S-Face Medical College. Then 3D modeling using medical imaging software. Then you 3D print the skull using FDM 3D printing process. And you evaluate the orbital volume 3D printer scan 3D CAD model, and you do analysis and validate the results. So you collect the CT scan image. Once you collect the CT scan image, Then these are the various software that we are going to use, like Radium, Dicom, Invisalign, Blender, Autodesk, Mesh Mixer, Flash Print, and Stata1 Maxillo. These are the various software that we are using here. And what is the Radiant Dicom viewer is using simply you take the CT scan image and import into it. You can have a quick overview of the 3D model of the CT scan such that the research can be carried out over the specific area of interest. That's what you use the Radiant Dicom viewer. And then the DICOM images are converted in 3D CAD model with the help of Invisalign 3, which is again open source software. So what are the various steps involved in doing this process? First step is the medical image coming from the CT scanner consists of grayscale information. First, the DICOM files are to be loaded into DICOM browser in the Invisalign. So you incorporate into this Invisalign software these DICOM files. Then after importing the files into the software, all the slices are shown in 4 windows. These are the 4 windows, just like you have in your conventional CAD software. You have front view, top view, side view, and isometric view. Here also you have axial view, sagittal, coronal, and isometric view. So this you get from this you get this is like your top view, front view, side view. So this is the top view, this is the side view, this is the front view, and based on which you can understand what is your region of interest, what is the area in which you want to build the implant or develop the picture. So you try to select this, crop it, and select, so that you get finally how you get one is you select the threshold value. So for each part of the human body, you have some threshold value, nothing but you have pixel. When you take a CT scan, you have what different layers. So each one will have what you have is the picture. The photo, the image will be in the store in the form of pixels, the values. So the bone will is having higher value, so it appears bright. You can see the green color. Bone is having higher, and other tissues will have different colors, right? So what is your region of interest? Accordingly, you have to select that range. Once you select the range, only that portion will get a growing, and the other portion will get eliminated. Segmentation will done, other portion will be eliminated. That's what happens here. So what we have done, we have selected bone as a preferred metal because our fracture happened to the bone. So you take that bone and you obtain threshold value of minimum 226, maximum 3071, and you define the bone region. You get this shape. You get this particular object. This is what you got here after selecting this range. These are the only pixel values that we recognized, right? And then we have exported the 3D surface and saved it as .stl format, such that 3D CAD model can be 3D printed. So you have done it. And cleaning the unwanted region, discontinuous areas using Blender software. So using Blender software, computer graphics software, use it for creating animated films, visual effects, and etc. You import the .stl file into the Blender software, right? Then cleaning the unwanted regions, you remove the unwanted regions, discontinuous areas using Blender software. Then you get what you call unwanted regions. You get invert the selection. This will select all the unlinked one. That is all discontinuous points you get here. So these continuous points, you have to remove, you have to eliminate all of them. So these eliminate all of them. Then you join, and deleting the unwanted areas gives a finer finish to the 3D CAD model, which helps in building a perfect 3D medical model. So you remove this unwanted region, so you get this image. But how to fill up this unwanted region? Again, you are going to use another software called Autodesk Mesh Mixer. That will be inspecting what are the repairs and errors, what are the missing things that are there here. Those things it will select and remixes with specialized tools for 3D printing, right? So before you 3D print, it will try to fill up those discontinuities which are removed, and the creation of 3D mashups. It is used to work with triangular meshes and refine the 3D model. Import the STL file into Mesh Mixer software. Then go to analysis section. In the left pane, click on inspector. This will show all the errors present in the STL file. Now click on auto repair all. That will make to remove all these errors that you have here. So once you remove this, after errors are removed from the STL file, using Mesh Mixer software, you export into STL file. So once you remove error, you export into STL file. Once you do it, then you slice and orient the STL file using Flash Print software. So before you print into the machine, yesterday as we discussed the process chain of 3D printing, before you print into the machine, you have to slice and orient the STL file using the Flash Print. In the Flash Print software, you have to orient the STL file, right? So you have to slice it and orient in the STL file with the proper layer thickness, etc. So these are the orientation. We have plane XYZ 0 degrees, plane X 270 degrees, different ways. So I can find out what is the build time and total metal consumption. So build time with this one is 21 hours 16 minutes. I selected this 21 hours 16 minutes as the time for building the part. So now we have oriented the part like this. You can see these are the support structures that are coming here. So if you see that our orientation should be selected in such a way that are minimum support structures. So if you have minimum support structures, definitely your part is built, because if the support structure is there, you have to remove those things from the main part. So when you remove it, there is a point of contact, ulceration, kind of roughness. You have to do some post processing. So without affecting the part stability, you will see that your support structure is minimized, right? And then you slice and orient the STL file using the flash print software. Then we have sliced and oriented. I can now, before the part is printed, I can get 21 hours 16 minutes is the time, that print time, and material is 41.52 meters. So this is the machine in which I am going to build the part. So this is what printing you get this part. Preoperative medical model in flash forge printer. So this is the preoperative medical model you get here. And this is what I got the entire before operation, how that fracture happened, to understand that this is how I got the part. So this we will be giving it to the doctor. Now doctor will be present, selecting these landmark points on the this is called contralateral side, and this is your actual fracture region. You will measure the distances between them. So you will estimate what is the volume or inside this without fracture, normal eye. But here you will before after fracture, what amount of volume that replaces. Naturally, this volume will be higher than this. Now, perform operation for the patient and put all the mini plates etc. Perform it and see that this volume gets uh, for months. Again, we'll take a CT scan image. Again, we build this. Already we got this. There is no fracture on this side. 3 months we'll take the printout, and the left side I have taken. Now I'm taking same way I will do value converting in STL file things I do, and this is the left portion of the thing I get here. So printing process post-operative medical flash forward, estimated time 10 hours 11 minutes, and estimated weight is 19.15 meters I got here. So this is what you can see after operation after 3 months. See how that bone has grown, and these are the mini plates. Actually, there are 10 mini plates which are fixed because we have printed in our FDM 3D printer. We got this as a PLA material only. But this is how this joint, this skull portion has been joined. And again, you will put the landmark points here and measure the distance. You measure the volume, right? So the first thing, and we put both of them, and these are the landmark infraorbital, forward medial orbit, and zygomatic. I have taken this, and then I measured all these distances. So you can see how we use a digital vernier calipers to measure all the distances of the points, and both the left and the right eye we measured. And even we use a software also in not only 3D printed. We started on software and measured this distance volume on the contralateral side, measure the volume on the fractured side before operation. Then same thing I measured after operation also, we measured the fractured side, right? So what we got is operation, after injury fracture, this amount of volume got 29.771. This is the volume of the contralateral side, 27.086. This is on the using this software I got this, right? Similarly, after operation, after 3 months, we measured this 0.335. So it has 27.086. Earlier it is 29.7. So what we concluded is, from the above results, it is concluded that the orbital volume of unfractured orbit, fractured orbit before operation, fractured orbit after operation is found to be 21.04 cc, 29.04 cc, and 21.69 cc respectively. That means what you can see, the unfractured side volume is 21.04, and the fractured side before operation is 29.04. After 3 months of after operation, after 3 months, it was measured to be 21.69 cc. So you are able to restore to 91.88%, which is a good sign of restoration. This we got in the 3D printed model. But in the CAD model also we have done the same way, but we found the restorations to 90.67%. So we can say the 3D printed model has given better accuracy than your CAD model. This is how 3D printed model helps in evaluating the orbital volume during mid facial fracture. Like this, we have done for 20 cases too, so that we can generate a procedure. We can tell doctor how best way he can improve the operation performance, so that this restoration can be improved further to 95, 96, so that it will be almost normal like the original one. That's what our aim is. So this is how 3D printing helps in orbital volume analysis. So let us see the case two, development of a 3D printed model for cranioplasty surgery. So you can see cranioplasty is defined as a neurosurgical project to cover an injured bone in the skull. This procedure is carried out. So cranioplasty is nothing but the skull. If you have some injury, in that injury portion, you have to put an implant. So that implant you have to do it. This procedure is carried out in order to protect and restore intracranial structures and to restore the appearance and psychological stability of the patient. So you see in this case, a patient who's got injured here to the left parietal region. You can see this is the left side parietal region of his skull. So here you have to put an you see the below this is simply skin was stitched to it, and you can see there is a complete implant you have to fix here, right? So this our idea is how to we have to develop this implant, right? So for this we consider 16-year-old patient was there, and what is the physical model we are going to create a model of this one, that is this is we use a polyamide SLS technology, we can create this model of this, and this can be used as an implant. Indirectly you can make it as a pattern and make a mold, and in that using this pattern you can make a mold, and once you remove this pattern you pour the biocompatible material like polymethyl methacrylate that will be used for bio cranioplasty surgery, right? So traditionally we asked doctor how they used to perform this operation without 3D printing. Earlier they used to put an on the head and a basket and apply algae, remove hair and apply algae, and with the skill set of the doctor, the highly professional doctor, senior doctor, they used to have their own skill set, and they used to take an impression of this, how that fracture happened. So with this, they will use to understand, okay, this is the type of thing you have. But what is the problem with this is, it all depends on the skill of the doctor, not so accurate. And also, because it is not accurate during the operation, they have to do some filing, some other work, extra work they have to do. So that is consuming a lot of time. The other thing is, the patient before actual operation is performed is made to sit in the operation theater for getting this impression itself. For getting impression itself, he has to wait for 8 hours, 9 hours, like that. So that is again agony for the patient, for him, right? So that case, what we have asked is doctors to give the CT scan image. So he has given the CT scan image, and I told in the earlier project we told how we have done the biomedical modeling, applying the given threshold value, that is a bone in our case. So using the threshold value, now we are able to generate this model, right? So this model is generated. Sir, I am audible, sir?
You are audible, sir.
Hello?
You are
Sir,
audible, sir.
your recording is still on, sir.
So, sir, I'll cut later. No problem, or I have to stop here only. Recording.
You stop here only, sir.
Okay, sir.
Then you can record later. Surgery. So generally our human body, our spine is very important portion of human body, which will support the entire body. And here you have different regions of the spine: cervical vertebrae, thoracic vertebrae, lumbar vertebrae, and sacrum. So lumbar vertebrae we have 5, 1, 2, 3, 4, 5. So the entire body weight will come here, and there is always a scope of degeneration. So you can see here the lumbar spine, you have first lumbar, second lumbar, third, fourth, fifth lumbar, and intervertebral disc you have in between these lumbars. So this intervertebral disc will be creating, right? So after degeneration, what happens is I'm going to show you, right? So this is how it appears. Inside this one, you have a what you call a nucleus-like thing, a gel-like substance will be there, which will be helping as a lubricant, right? So if this gel-like substance, because of degeneration, this annulus ring it gets some cracks. This gel will come out and press the nerve. So behind your this one, you have a tunnel through which all nerves will pass from your head to other portion. So this will come and hit this what you call the nerve. So because of it, the blood flow will stop here. So spinal nerve blood flow will stop. So this is a normal disc, this is a degenerative disc, this is a bulging disc, etc. So what happened? Let us see with this video. Let us understand how this operation happens.
Atlantic Spine Center offers endoscopic lumbar discectomy.
Are you able to hear the voice, sir?
The spinal
Yes, sir.
column
Yes,
or
sir. Clear,
backbone
sir.
is one of the most important parts of your body. It provides the main support, allowing you to stand upright, bend, and twist. "33 individual bones interlock with each other to form the spinal column. The vertebrae are numbered and divided into regions. C1 through C7 cervical vertebrae form your neck, support your head and neck, and allow you to nod and shake your head. T1 through T12 thoracic, that's the 12 vertebrae that are joined by ribs to form your rib cage. L1 through L5 lumbar, your 5 sturdy lumbar vertebrae carry most of the weight of your upper body and provide a stable center of gravity when you move. 5 vertebrae of the sacrum and 4 of the coccyx are fused. It makes up the back wall of your pelvis. Between each of the movable vertebrae is located the intervertebral disc. Intervertebral discs consist of a thick outer layer with a crisscrossing fibrous structure, annulus, that surrounds the soft, gel-like center, the nucleus. Discs function like shock-absorbing springs. The annulus pulls the vertebral bodies together against the elastic resistance of the gel-filled nucleus. When you bend, the nucleus acts like a ball bearing, allowing the vertebral bodies to roll over the incompressible gel. Each disc works in concert with 2 facet joints, forming a spinal motion segment. The biomechanical function of each pair of facet joints is to guide and limit the movement of the spinal motion segment. The surfaces of the joint are coated with cartilage that helps each joint move smoothly. Directly behind the discs, the ring-like vertebral bodies create a vertical tunnel called the spinal canal or neural canal. The spinal cord and spinal nerves pass through the spinal canal, which protects them from injury. The spinal cord is the major column of nerve tissue that is connected to the brain and serves as an information superhighway between the brain and the body. The nerves in your spinal cord branch off to form pairs of nerve roots that travel through the small openings between your vertebrae, intervertebral foramens. This is the condition of a normal lumbar intervertebral disc. As a disc degenerates and breaks down, the inner core can leak out through the outer portion of the disc. This condition is known as a disc herniation, which puts direct pressure on the nerve. Lumbar herniated disc symptoms include low back pain, legs and buttock pain, leg numbness, and tingling. Endoscopic lumbar discectomy is a minimally invasive procedure for treating lumbar herniated disc. First, a thin guide wire is placed under X-ray control down to the
This is
involved.
how it happens. This gel will come out and press the nerve, and the blood flow will stop here. So now you have to remove this excess one. What the gel is there?
Level of the spine. A tapered dilator is inserted over the guide wire. A small tube is inserted over the dilator to create a portal to the herniated disc. The endoscope is placed through the tube and the discectomy is performed. Using special instruments, your surgeon can now microsurgically remove the herniation, thereby relieving nerve root compression. The incision is closed with a stitch or two and the procedure is complete. Advantages of endoscopic lumbar discectomy include the following: minimally invasive, short recovery, high success rates, minimal to no blood loss, preservation of spinal mobility, small incision and minimal scar tissue formation. Patients are typically able to go home in a few hours.
So here you understand now the
Atlantic Spine Center.
criticality of this
Mesothelioma.
operation. So our aim is now before the doctor performs the operation on the actual human being, he has to simulate, he has to practice on a kit. So our aim was to develop this kit, lumbar dissectomy kit. This so that the young doctors who don't have the experience also can practice on this before they perform the actual operation. So we constructed the entire model that spine, lumbar disc L1, L2, L3, L5. Already a model is there with the doctor. We scanned it, developed the model, and then we built our parts. So lumbar vertebral printed using ABS we made printed. And to distinguish different parts, we made with 3D printed this lumbar intravertebral disc using thermoplastic polyurethane. And 3D printed a spinal cord using thermoplastic polyurethane metal TPU. We made both of them. Then we assembled them, and then we have done this work. And we have to put in a box, and so that inside this box, no, that the doctor will be putting a needle and planning the rehearsal, the entire thing here on the kit itself. That's what you can use 3D printing for that application. Let us see how additive manufacturing can be used for solving this conjoint twin separation case. Let us see how you can use it. Is a very interesting operation performed in 2002. The patients are Maria Theresa and Maria diseases were born in 2001 in Guatemala. So together they weighed 4.4 pounds at birth, and despite their small size, they are very healthy, but except for being joined at head. So over the past years, the girls have remained healthy and happy, but they have been severely restricted by that. They cannot move easily, right? So the challenge for the physician is separating the conjoined twins is one of the most complicated procedure imaginable. You have intertwining bones, nerves, blood vessels, and other tissue force in common between both these girls. Forces doctors planning such an operation to abandon everything they know of normal anatomy and chart from scratch the way each of these unique pairs is arranged. But the veins that drained the blood were interwoven and fed into each other's circulatory system. The most complex part of the operation would be to sort out these veins and reroute each girl's blood supply. So here additive manufacturing plays very important in planning this surgery. So they have taken X-rays that showed the girl had a separate fully developed brains but also has crisscrossed blood vessels. Tracking those blood vessels on the two-dimensional X-ray is impossible. So the surgical team, which was headed by Dr. Henry Kawarmota, Director of Craniofacial Surgery at University of California, Los Angeles, and Dr. George Lazarus, Director of Pediatric Neurosurgery at the Mattel Children's Hospitals. So the doctor and the team had used rapid prototypes previously and convinced the lead surgeon that such models might be useful in this case, enabling the plastic surgeon to practice how to separate the two girls. So using 3D printing, they produced all these models and they performed this operation, simulated this operation on the model. Then once they got confident, they during the operation also they have put the models along with that die. Then how to slice those two heads, separate those two heads is very challenging. So they have to do several rehearsals, different ways, so that the minimum damage happens to the and then the patients, right? That's what is the aim. So they use Mimic software for developing the 3D model. They use object tempo rapid prototyping system. Yesterday I've shown you in that Hollywood movies. Object tempo rapid prototyping system building parts by selectively jetting tiny droplets of acrylate, photopolymer, and then curing the drops layer by layer. So unlike stereography, which uses primary building material for supports that must be made, cut or sand away. So once a part is complete, this gel-like support material can be wiped off or removed by using water. So object tempo, three parts are built, one of each girl's skull and one of the junction between the two. So you have the parts. So it took 24 hours to build each of these parts. So each of the part they built 24 hours. They have sliced and they understood how these interweaving things happen. A model of the region where the two skulls connected so that the surgeons could study the maze of the blood vessels. See how they are planning the surgery on this table. So a plastic surgeon rehearsed with the models to help plan how they would arrange to cover with the operation. Main purpose lead surgeon Henry Comer. No matter how good how your 3D graphics are, there is nothing like a model in your hand. So this is how the planning is done. Let us see this video, how this operation is done. Entire video. It took the operation time was nearly 10 to 12 hours to do. And during the operation, they put all these models beside that table, operation table. They understood how to do this. Let us watch this video and understand how additive manufacturing can be used for separating this conjoined twins, such a complex operation.
Their historic surgery
Are you able to
captured
see the
parts
video
right
and
away.
audio, sir?
And
Yes,
the
sir. Loud and clear.
imagination, some of the world's greatest
You
medical
are able to hear the
minds.
audio also?
Audio
Apparently,
also,
these
sir.
are two distinct personalities, two distinct human beings. That unusual situation of being in a biological prison, essentially.
Maria Teresa and Maria de Jesus are joined at the skull, the rarest of conjoined twins, and the most difficult to separate.
We could look at the venous system, which was clearly the problem. The veins were connected between the two twins, the arteries were not.
We needed to separate them because such twins typically die between ages 5 and 10 when the brains expand and start squeezing on each other. So this operation was necessary to give them a chance at a happy, healthy life.
Two prestigious hospitals turned the twins down, but doctors at UCLA felt there was enough medical evidence to support a successful separation. Neurosurgeon Dr. Jorge Lazarus assembled a team determined to free them.
I felt, based on the confidence transmitted by Itzhak and John, that this could be possible, that this was possible, that the surgical procedure was the ethical and the reasonable thing to do for those girls.
Doctors took dozens of pictures, CAT scans, MRIs, angiograms, but they needed something more.
A model which was built of the heads themselves, showing essentially the point of connection.
So we finally hooked up with this firm, BMI Biomedical, Modeling Incorporated in Boston, and they sent us the models back.
From images sent by the doctors, biomedical modeling created a perfect replica of the twins' heads.
These models are very important to doctors. They, for the first time, allow doctors to have a physical, three-dimensional visualization of the patient's particular anatomy.
It was a difficult, labor-intensive process to build the perfect models. But hearing the doctors and the hospital at UCLA had donated their efforts, biomedical modeling decided they would donate their efforts to save the twins too.
Once we have the data, we bring it onto our computers, and we see the familiar CAT scan images that people are accustomed to seeing. And we take those and we filter out the parts and tissues that we want to be included in the biomodel. And once they approve it, we go ahead and we decide to fabricate it. And that's done. The computer model is then sliced back down into the similar layers that you see in the beginning, where you see the cross sections of bone. And that's put onto a machine that literally builds up the model layer by layer out of plastic. So the layers are extraordinarily thin, as thin as a human hair. And they start off usually as a liquid. And that liquid is solidified by ultraviolet light. And once it's exposed to the ultraviolet light in those patterns, they solidify and they stack one on top and they glue to the layer below. And then when you're done, what you have is an actual 3D plastic model of the anatomy.
To coordinate the effort, biomedical modeling worked with Dr. Bill Clarihue, one of the nation's most respected anaplastologists. Dr. Clarihue builds craniofacial implants and prosthetics for American veterans. He too volunteered after hours to help doctors with the twins.
I was able to view the information on the computer and show the surgeons exactly what they're going to get as far as a 3D model is going to end up looking.
We will remove the bone 60% up to here.
At UCLA, neurosurgeons and plastic surgeons work out their strategy together.
In the beginning is this area exposed, and then
The critical factor in trying to separate them was the blood vessels. And the neurosurgeons had sort of worked that out, and they thought that they could do that. Then it became a problem of getting everything covered.
The twins were separated. They could not simply cut the skin right along where the skulls were joined together. If they did that, they wouldn't have flaps of skin to cover the scalp afterwards and allow the twins to recover.
These are the flaps that we've designed based on this three-dimensional skull that's rendered from the CAT scan.
It's interesting because they're using, it's like paper cutouts. They were using felt to mark their flaps. I mean, it looks like you're playing with paper dolls, but that's what they're doing because
You
that's
have
the
the
best and easiest way to
operation
do
time they
this.
are
They
doing.
could practice
Beside the
on
operation
those skull
table, they have
models
put this model.
with their surgery prior to doing the surgery. I mean, how often can you hold the skull in one hand and operate on the skull in the other? This is the only way this can be done.
The model of the head, please. I'd like to have a story that
Throughout the 23-hour marathon surgery, the
23-hour
biomodels were
operation
used from
time.
beginning to end.
First thing that will be done is this flap will be flipped towards me.
Right.
These models that we did our flap designs on were made off of CAT scans, CT scans. They're highly accurate. I mean, these models are very, very accurate. When the time came to make that first cut, we made it along the patterns that we had designed. And then we realized, I mean, then it really sunk in on me was there's no turning back.
And to have things turn out so well is very gratifying. To see the impact on the world. I mean, literally on the world. I would have never, in my wildest dreams, guessed that it would have this kind of impact.
We are really delighted to have been part of this very heartwarming story. Joined at the head, they would never be able to walk or stand or even eat normally, and were likely condemned to die between ages 5 and 10. Now they have a chance to be two happy, healthy individuals, and we look forward to hearing about their growing up and their successes in life.
Go to the weddings.
Within months, they are on their way back to Guatemala. Two healthy little girls, still on the mend, but with the promise of normal, healthy, and independent lives.
So I hope you can appreciate now how 3D printing can be used for this very critical operation.
Sure, sir. That was
Are
very
you able to see the
interesting.
screen, sir?
That was very interesting. Yes, sir. I'm able to see.
Yeah, that's what 3D printing helps in solving such very critical cases.
sir,
So
sure.
save the humanity. So additive manufacturing has got the capability of saving the humans from all critical surgeries, the difficulties you face. There are another very small interesting case study we have done for functional finger prosthesis with our BE student Shashank. During his summer internship, he has done this work. So you see, finger prosthetics are there only in the cosmetic purpose. The main of this project is design a finger and make it functional such that it can hold or grip objects. The finger movement is achieved by motor and the finger is manufactured using 3D printing. So for such cases, you require a full finger you have to make. So you have these parts and you made all these parts joined together and you can put wires across this and that can be controlled by a PCB using which you can have the movement. I am going to show that video also. This we have done in our lab. We have printed these fingers and joined and this can be used for these people also. Let me show that video also. Finger we made, you connect it to some Arduino board circuit. It can operate. This part of this finger is printed using 3D printing. Connect. So this is a very crude stage. We have to further improve this. If you get a signal from the brain, you should be able to operate. This is a further work you can do. At present, this is the stage. This portion you can print in 3D printing. So this is a small work we have done using 3D printing technology. So with this, I finish my this. What is the future of EM? This is called Gartner's 3D printing. So what it says is initially for any new technology that comes, there is a lot of hype. You'll think it will solve every problem. It is so great, everything. But after some time, you find the limitations of those things. So the limitations makes it to come down. The demand of that will come down. But after some time, again, what happens? You overcome those limitations, and slowly the graph will start picking up. So we are in this area. This is what we found the most recent graph published by the firm in 2017. So you can see, and this is what happened. This took more than 10 years to reach to this curve. Now we are in this stage. We are about to drop for disillusionment. You find, oh, this is not working. So this technology like this you get. But finally, once you start overcoming these limitations of the technology, so as on July 2017, we are now reaching the better saturation point, correct level, maturity level of the technology is coming. So 3D printing now, it is going to be there and it is going to solve a lot of cases, especially biomedical aerospace applications. It has got high potential application. Automobile also, you see a lot of cars, automobiles nowadays you see. You will see that there is a regular change in the tail lamps or in the OVRMs, overview rear mirrors or the front bumper or the dashboard. Everything now is it's a car is also evolving itself like anything, like cell phone. Every 15 days you get a new model. Car is also every month you are getting a new model which looks different. How this is possible? How you can do it very fast? The change in the product design. So earlier also your designers are there who can create things with a creative idea, but the manufacturing is unable to support such creativity, is unable to produce such complex products. But using 3D printing, we can produce such a complex products within less time. So that's how the new technology is helping the evolution of new types of cars. Otherwise, earlier, if you make a chain tail lamp using the conventional process, you will take a lot of time to produce that one. Because converting that idea to a form, physical form itself is a difficult task. In additive manufacturing, you may ask questions, sir. It cannot do mass manufacturing. Yes, using additive manufacturing, you can produce a prototype, make a mold, injection mold, anything. And then from there, you can produce things in large numbers. So making that initial mold, which is complex, using conventional method is very difficult. But using additive manufacturing, you can make it and then you can run that. So this is the future of additive manufacturing. It's called Gartner's 3D printing car. So I thank my director, principal, and head of the department for their support in conducting this research. I also thank the team of doctors who worked with us. So, like Satish from CMF, Rajesh from Neurosurgeon Yashoda Hospital, Suresh Kumar, Maxillofacial, Dr. Abhinandan Potturi, who is also another speaker in this program, for their support. We are all work together as team and solve such critical cases. Thank my students also and team of CPTDM, all the students who worked with us in solving these cases. As I feel that the students and faculty, if you can put proper interest in research, you can solve such wonderful cases very easily. If you have any queries, it is open for discussion. This is my contact. Thank you very much for your patient listening. I hope I started late because due to some other reasons, but I think I lived up to your expectation morning session. So I made you to understand the importance of additive manufacturing biomedical. Thank you very much. If you have any questions, it is open for discussion.
Thanks for your wonderful sessions, sir. Always your sessions were resourceful and interesting as well. There is one
Thank you,
question.
sir.
There is one question from Nitin Chandra Manas, sir. Is there any health issues? Is there any
In
health issues
Jain
for
GL,
long term after implant?
in crown and bridge practice, when we use
Is there any health issues for long term for after implant
Salman
surgery?
Shah Qadri. So, right, I am going to see that, sir. Is there any health issue for long term after implant? Which cranioplasty implant you are talking about, Mr. Chandra Manas, Nitin Chandra Manas? Yes. No, as such, until now, we put in 2013, there are no issue until now. So until there is some kind of other infections happen, there may be a problem. But until now, there is no any. We did not hear any kind of issues from that implants. And Jain JL is telling in crown and bridge practice when we use SLS, DMLS, the connection region, pontic region, and retainer walls are coming with different bulk of thickness or thickness. Thicker region will undergo more contraction upon cooling. This can lead to distortion of framework. The parameters adjustment in machine for percentage of contraction for any metal may be same. How we can prevent this kind of distortion? Crown and bridge practice, especially in long span bridge and full mouth rehabilitation, it seems a challenge. Without compromising precision, is it possible to print long span framework? Sir, could you please explain about this? A very big question. So dental applications, you mean to say this is having SLS or DMLS? The SLS you not use, no metal based one, use either DMLS or SLM you use. So definitely you have to take care of the shrinkage effect of these materials which are using for that application. Based on the shrinkage allowances, you have to plan your structure and you can to produce that one. So distortion, how to prevent it? You have to take care of the shrinkage, how the distortion happens based on the material. For example, you're using titanium or you're using nickel, cobalt, chromium, or some other biocompatible stainless steel. Also, you have some alloys which are biocompatible. So when you have to take care of those shrinkage allowances and try to prevent it. Okay. Please share your contact details. Already I given in my slide. It's you can send me a mail. My mail ID is sivaramakrishna.l@ucou.edu, or you can use my contact number 98498670046. But that may be instead of directly calling, you can put an WhatsApp or send them an SMS, or better to send a mail. When you call, maybe in meeting or some other thing. So any more questions, sir? Anyone want to interact directly? They can also switch on their video and interact.
Yes, any questions? If you want to ask any questions, queries, or discuss something, you can directly ask speaker. Our speaker is very enthusiastic to give the answers to your questions. Please mute yourself, unmute yourself, and please ask the questions.
You can give feedback also. If you have anything to tell, you can also give. You can also give suggestions to me how to improve further. Let them introduce themselves and they can speak.
So there is one question. How can we print endoscopic disc using polyjet?
Endoscopic disc.
Disc. I think they are asking about the disc which you have showed in the endoscopic.
Yeah, we have used FDM.
FDM.
You can also go for a polyjet, but why it's very costly, So we went for FDM process. Basically, it is a model. So we are not putting anything inside human body. So for practice only, we are making that kit. So making it FDM is easier, but you can print in polyjet also. Same model, you can convert STL file, you can send it to the polyjet and you can print it. Yes.
There is another question from Mr. Khalid. What material used for printing finger as you shown in the video? I think they are asking about your research work which you have carried on in your CPDD answer. Which material is used for printing the finger printed?
That is, we use PLA, polylactic acid. PLA, finger prosthetics.
Any other questions?
Okay, if not, I can.
Please raise your hands or you can ask questions. Sir, there is a question from Mr. Salman Shah Khadri. Can we sense and eat as usual if we implant the teeth?
What, sir?
After implantation of the teeth, sir, so we will going to sense the food or taste like that he's asking. Whether we're going to have any
After implanting the
teeth,
uh,
we will going to have the same sense before the implant, or are we going to have some effects after
okay, the implant, how accurate is it, as good as the natural teeth? That
natural
was.
thing?
Yeah, mostly with 3D printing, you are getting almost, cannot be 100% natural teeth, but it's now almost nearer, it appears like a natural teeth only. The material also now improved, and it's like a natural teeth, the functionality, everything. But 100% you cannot say it's like a natural. Definitely,
functionality.
it is better than the earlier versions of implant, which was made with other conventional.
So we
Far
can
better than earlier. Accuracy wise or finish wise, everything is better. But only cost is the only factor, which is higher than the conventional.
so we
But
will
the
not
durability and everything is higher
going to have
because
hmm. we will not
because the accuracy is good. No, need not again remove that implant and put it every time.
Yes,
So
sir.
the accuracy is good. That's why the longevity is also high using 3D printed.
So is there any questions? I once again thanks Dr. L. Shivaram Krishna, Joint Director, Associate Professor, Usmania University, Hyderabad, for giving a wonderful, resourceful, and interesting lecture on biomedical applications of 3D printing. I would like to highlight some of the key points. He first given the necessity of 3D printing in the biomedical applications, giving introduction about the softwares, Blender, Mesh Mixer, and giving the introduction of the flash force printer and the fractures in the skin or the skull using the cranioplastic surgery. And he has given a wonderful difference between the traditional cranioplastic surgery as well as the nowadays which we are going to use using the 3D printing. And one of the interesting session was sir endoscopic lumbar dysautonomy. That was again a wonderful lecture and interesting, and with various case studies like conjoint case which is using the mimic software and stereolithography process. Now the USA they have solved the problems. The other case studies like your Sunshine Hospitals and Care Hospital using this 3D printing technology, you have solved the real challenging problems which was faced by the patients. So I once again thank sir for your wonderful and interesting session. Hope most of the participants have benefited, and they will going to use your this work, and they can proceed or carry forward your work in near future. I thanks once again, sir.
Thank you, sir.
Thank you, sir.
Thank you. Thank you for the opportunity. Thank
Thank
you.
you, sir. Thank you.
Right. Right.